Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The year 1938 marks an epochal juncture in the annals of nuclear physics. Within the austere laboratories of the Kaiser Wilhelm Institute for Chemistry in Berlin, Otto Hahn, Lise Meitner, and Fritz Strassmann conducted experiments that would irrevocably alter both scientific understanding and the geopolitical landscape. Their collaborative effort, culminating in a publication detailing a new type of nuclear reaction, revealed the previously unimagined phenomenon of nuclear fission, a discovery fraught with both profound promise and existential peril. Decades prior, Ernest Rutherford's pioneering work on the atomic nucleus, particularly his gold foil experiment, had established the dense, positively charged nature of the atomic core. This foundation, coupled with the subsequent discoveries of the neutron by James Chadwick in 1932, provided the necessary conceptual groundwork for understanding nuclear structure and potential transformations. Enrico Fermi's group in Rome had been diligently bombarding various elements with neutrons, observing that many transmuted into heavier isotopes, often emitting beta particles in the process. This line of inquiry, predicated on the belief that bombarding uranium, the heaviest known element, would lead to the creation of transuranic elements beyond uranium in the periodic table, served as a crucial antecedent to the Hahn, Meitner, and Strassmann experiment. The experimental setup within the Kaiser Wilhelm Institute involved meticulous attention to detail. Hahn, renowned for his expertise in radiochemistry, meticulously purified the reaction products resulting from neutron bombardment of uranium. The technique required the dissolution of uranium salts in appropriate solvents, followed by selective precipitations to isolate specific radioactive fractions. Barium salts were added as carriers, substances that coprecipitate with radioactive isotopes, facilitating their isolation. The ingenuity resided in the application of rigorous analytical methods to definitively identify the resulting isotopes. Early experiments indicated the presence of radioactive species that exhibited chemical properties similar to radium, an element lighter than uranium. However, upon closer examination, these species displayed behavior remarkably akin to barium, an element with a significantly smaller atomic mass. The meticulous chemical separations, coupled with carefully calibrated radiation measurements, revealed with growing certainty that the presumed radium isotopes were, in fact, isotopes of barium. This finding proved deeply unsettling, as it challenged the prevailing understanding of nuclear reactions. At the time, scientists believed that nuclear transformations involved only minor changes in atomic mass, with particles akin to alpha particles or beta particles shed in the process. The idea that a uranium nucleus could essentially split into two significantly lighter nuclei appeared physically impossible under existing theoretical models. Lise Meitner, an Austrian physicist of Jewish heritage, had collaborated closely with Hahn for over 3 decades. Faced with increasing persecution under the Nazi regime, she was forced to flee Germany in July 1938. Taking refuge in Sweden. Despite her physical separation from the Berlin laboratory, Meitner maintained constant communication with Hahn, providing invaluable theoretical insights and encouragement. She and her nephew, Otto Robert Frisch, a fellow physicist in Copenhagen, grappled with the perplexing experimental results. Drawing upon Bohr's liquid drop model of the nucleus, they recognized the possibility that the uranium nucleus, upon neutron capture, could become highly unstable and undergo fission, splitting into 2 smaller nuclei. They calculated the energy released during this process, demonstrating that it was indeed substantial, originating from the conversion of a small portion of the nuclear mass into energy, consistent with Einstein's celebrated equation, energy equals mass times the speed of light squared. The theoretical explanation, published in Nature shortly after Hahn and Strassmann's experimental findings, provided the crucial conceptual framework for understanding the observed phenomenon. The term fission was coined by Frisch, inspired by the biological process of cell division. The initial impact of the discovery was primarily confined to the scientific community. Physicists around the world immediately recognized the profound implications of nuclear fission. It opened up entirely new avenues for research into nuclear structure and nuclear reactions. Furthermore, the enormous energy released during fission hinted at the possibility of harnessing this process for practical purposes. Enrico Fermi, then at Columbia University, promptly initiated experiments to investigate whether fission released additional neutrons, thereby potentially sustaining a chain reaction. Within months, several laboratories had confirmed the emission of secondary neutrons, solidifying the prospect of controlled nuclear chain reactions and, consequently, the development of nuclear power and nuclear weapons. The influence of the 1938 paper resonated far beyond the immediate scientific community, the revelation of nuclear fission, and its potential for enormous energy release, rapidly captured the attention of political leaders and military strategists. The nascent understanding of the possibility of nuclear weapons prompted grave concerns, particularly given the escalating tensions in Europe. Albert Einstein, upon the urging of Leo Szilard, penned a letter to President Franklin D. Roosevelt, warning of the potential for Germany to develop atomic bombs. This letter played a pivotal role in initiating the Manhattan Project, a massive research and development effort spearheaded by the United States during World War II, aimed at developing the first atomic weapons before Germany. The direct applications of nuclear fission, initially envisioned in the form of weaponry, rapidly expanded into diverse domains. Within a decade of the discovery, the first nuclear reactors were constructed, harnessing the controlled release of nuclear energy for the generation of electricity. Nuclear power plants arose, offering a promising alternative to fossil fuels, although also exhibiting unique challenges regarding safety and radioactive waste disposal. Furthermore, radioactive isotopes produced through nuclear fission found widespread applications in medicine, industry, and research. Radioactive tracers are used to diagnose and treat various medical conditions, while industrial applications include gauging material thickness and sterilizing medical equipment. In research, radioactive isotopes serve as invaluable tools for studying chemical reactions, biological processes, geological phenomena. The Hahn, Meitner and Strassmann publication triggered intense scrutiny. The initial debates revolved around the interpretation of experimental results and the validity of the fission hypothesis. Some scientists questioned the attribution of barium to the fission of uranium, proposing alternative explanations based on contamination or experimental error. However, independent confirmations from laboratories around the world, coupled with a theoretical framework provided by Meitner and Fritz, rapidly dispelled any doubts. A more nuanced critique emerged later, focusing on the relative contributions of the individuals involved in the discovery. Lise Meitner's crucial role in the theoretical understanding of fission was initially overshadowed by Hahn's Nobel Prize in Chemistry in 1944, a controversial decision that has since been widely acknowledged as a significant injustice. Historians and scientists have diligently worked to rectify this oversight, highlighting Meitner's intellectual contributions and tireless dedication. The 1938 paper exerted a demonstrable influence on subsequent research in nuclear physics. The discovery of fission ushered in an era of intense investigation into the properties of heavy nuclei, nuclear reactions, and the fundamental forces governing the atomic nucleus. The development of the liquid drop model of the nucleus, pioneered by Bohr and Wheeler, provided a theoretical framework for understanding fission and other nuclear phenomena. The model envisions the nucleus as a liquid droplet, characterized by surface tension and electrostatic repulsion. This model predicts the stability of nuclei and the energetic thresholds for fission. Furthermore, the discovery of fission spurred the development of new experimental techniques for studying nuclear reactions, including neutron scattering, gamma-ray spectroscopy, and mass spectrometry. Numerous individuals and works exerted a direct influence on the 1938 publication. Rutherford's groundbreaking work on nuclear structure, Chadwick's discovery of the neutron, and Fermi's neutron bombardment experiments laid the intellectual groundwork for the discovery of fission. Bohr's liquid drop model provided a crucial conceptual framework for interpreting the experimental results. Meitner's extensive experience in radiochemistry and nuclear physics, coupled with her unwavering dedication to scientific rigor, played a critical role in the experimental design and interpretation. Strassmann's meticulous experimental skills and unwavering attention to detail were essential for isolating and identifying the action products. Conversely, the 1938 publication exerted a profound influence on subsequent research and technological developments. The discovery of fission directly led to the development of nuclear power and nuclear weapons. The Manhattan Project, spearheaded by figures such as Robert Oppenheimer and Leslie Groves, drew heavily upon the principles of nuclear fission. Enrico Fermi's construction of the first nuclear reactor in Chicago in 1942 marked a crucial milestone in the development of nuclear power. Researchers such as Glenn Seaborg and Emilio Seger made significant contributions to the understanding of transuranic elements, further expanding the periodic table and broadening the scope of nuclear physics. The development of nuclear medicine, with applications in diagnosis and therapy, owes its origins to the discovery of fission and the subsequent production of radioactive isotopes. The enduring legacy of the 1938 paper underscores the power of scientific inquiry to transform both our understanding of the universe and our capacity to manipulate it. The discovery of nuclear fission, a triumph of collaborative research and intellectual daring, continues to shape our world in profound ways. While the spectre of nuclear weapons remains a pressing concern, the beneficial applications of nuclear technology in medicine, energy production, and scientific research offer a testament to the transformative potential of scientific progress. The story of Hahn, Meitner, and Strassmann represents a complex interplay of scientific curiosity, political upheaval, and ethical considerations, serving as a perennial reminder of the responsibility that accompanies scientific discovery. One is reminded, with a touch of ironic understatement, that splitting the atom proved to be a rather divisive development.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.